In this video, we're going to go through all four of the mass spring system equations. Setting it out like this will help you spot the patterns between them and remember the equations. On the left, you can see we have free oscillations, and on the right, we have forced oscillations. All that means is that the free oscillations have their right-hand side set equal to 0, while the forced oscillations have a forcing term on their right-hand side, a forcing coefficient and either a sine or cosine function. Both free and forced are further broken up into undamped and damped. And all that means is that the undamped equations don't have a y prime term, whereas the damped equations do. Here, y is the displacement, the thing we want to solve for, m is the mass, k is the spring constant, and c is the damped coefficient that sits next to y prime, because only the damped equations have it. Both of these equations are also second order, linear and homogeneous, so we can use the characteristic equation method to solve them. Oh, and the units of k are, well, if we rewrite the damped equation as my double prime equals minus ky, and we use dimensional analysis, so mass remains as m, y double prime is a second derivative of displacement with respect to time, so acceleration, which is length over time squared, then the right-hand side also have to have the same units. We know that y is displacement, so it has a unit of length. So the spring constant k must have units of mass over time squared. For both the damped equations, c is the damped coefficient. We also have three possible scenarios. We have the underdamped case, where c squared is less than 4 km, and that's k times m, not kilometres. We have critically damped is when c squared equals 4 km, and we have overdamped if c squared is greater than 4 km. These will affect what our final solutions look like, and we'll get to some examples soon. Now we have the forced undamped case. Now this one's interesting because it's the only one that potentially comes with resonance. Think glass breaking from sound waves or bridges collapsing, all because the angular frequency equaled our lambda term inside the cosine function. When the angular frequency matches the intervals of our forcing function, the waves build each time just like someone being pushed at the perfect time on a swing. The person will swing higher and higher each time. So we'll end up with a function that gets bigger and bigger over time until eventually something breaks. So if our angular frequency equals our lambda inside the cosine function, we'll get resonance. If not, no resonance. This equation is also a second-order linear non-homogeneous ODE with constant coefficients, so we first need to solve the homogeneous case using the characteristic equation method. Then we need to use the method of undetermined coefficients to solve the non-homogeneous case, and then because the ODE is linear and our two solutions are linearly independent, we can use the superposition principle to write y equals y1 plus y2 to get our final solution. And for our forced damped system, we still have that c is the damped coefficient, and we have a second order linear non-homogeneous ODE with constant coefficients. So just like the undamped case, we can use the characteristic equation method to solve for y1. Then we can use the method of undetermined coefficients for the non-homogeneous case to solve for y2. Then because the ODE is linear and our two solutions are linearly independent, we can use a superposition principle to write y equals y1 plus y2 to get our final solution. Now let's model some examples. For our free oscillation undamped case, we're going to get a solution that looks like y equals some constant c1 times cosine of t plus some other constant c2 times sine of t, where y is our displacement and t is our time variable. You'll see that this is just going to continuously oscillate, just like this. Whereas if we have a damped system, it means it's always going to decrease with time. For example, written here is the solution to the ODE 4y double prime plus y prime plus 4y equals 0. This is an example of an underdamped system. Because it's damped at all, meaning it includes the y prime term, it's going to include an exponential decay term somewhere in the solution. But because it's underdamped, it's also going to oscillate using the sine and cosine terms until it gets to 0. So you should be able to see the oscillating part, but you can also see the decay part for this underdamped system. And we also have critically damped and overdamped. So now we don't have any oscillation at all. And critically damped just means it goes to zero faster than if it was overdamped. So a general solution for both of these would look something like y equals c1 e to the minus some function a of t plus c2 e to the some function minus b of t. So no oscillation and no sine and cosine terms. And now in the forced equations, we are adding a force into the system. So maybe it's a motor or maybe it's gravity. If we have the damped case, we're also dealing with something restricting the displacement, perhaps friction, which is going to make it want to go to zero. But we also have the force making it want to keep going. So it's a bit of a juggling act. So the system can experience damping but remain constant due to external force acting upon the system. So what it's going to do will depend on how strong the force is compared to the damping coefficient. It may eventually go to zero if the force isn't strong enough, or it may keep going indefinitely. If you liked the video, then please give it a thumbs up. If you found it helpful, then feel free to subscribe. I make regular videos on calculus, linear algebra, statistics, psychology, and physics. As always, thanks for watching.